So what is type 2 error? So we're not going to go over how to calculate type 2 error. Instead, the goal will be to understand what the idea is. Okay. So what is type 2 error? Type 2 error occurs when we don't reject a null hypothesis, when in fact it is incorrect. So the exact opposite of type 1. It is actually incorrect, a null hypothesis, but we fail to reject it. Okay, so that will be called a type 2 error. All right, so you'll see these pictures here, and you're wondering, what are these pictures here for? In order to understand a type 2 error, you need to understand one more piece that we're not covering in this course, but it's important. And you've already done when you did confidence intervals. In confidence intervals, right, you have to pick the margin of error, you have to pick the confidence level. The confidence level is the equivalent of the significance level that we just did. So you as a user have to pick that. But what is the equivalent of the margin of error in terms of hypothesis testing? Is there such a thing? And the answer is yes, there is. But it's a little more, I would say, complicated, because you have to make a kind of a decision sometimes people find at first strange. But I'm going to use the airline thing again. The airline thing was, okay, HO is P equals, and I'm going to write it as a percentage, and HA is the null alternative hypothesis is that we're trying to get it to be greater than 78%. So I'll put these numbers here as a percentages. So percentages, and that makes it a little just easier to look at. Here's the first thing you want to do when you're conducting a hypothesis test. You need to ask this question: how large of an effect will meet your goal? How large of an effect will meet your goal? What are you talking about? Well, let's look at what's happening here. Right now, online rate is 78%. We're trying to change a procedure to increase it to 78, something value greater than 78%. But the question is, so what value do you want? Like, what would make you happy? How much of improvement? This just says it's some improvement, but how much? Would 79% make you happy? Would 80% make you happy? Would 81% make you happy? 82%, what is making you happy? Just like the margin of error, you had to pick some margin of error, like how accurate do you want to make it? Well, here you have to decide how much of an effect size will make you happy. And so what you want to do is, obviously, let's say that 80% will make you happy. Then definitely if 80% will make you happy, then 81 will make you happy, and so would 82. So you want to pick smallest effect size that meets goal. So that's what you're trying to achieve. Okay, so I'm going to create a little scenario. So there's executive. So executive 1. So what happens with executive 1? Executive 1 determines that if we can increase to at least 85%, we met our goal. So that is executive 1 goal, is if we can get to at least 85%, we made our goal. So I'm going to call this 85%. Again, there's no such notation I'm about to use, but I'm going to call this PA, P alternative. And that means that this is now the thing that the executive wants to see. Of course, greater would be fantastic. So notice in this case, the effect size, cannot spell here either, effect size, is the difference between this number and that number, and you can see that it's 7%, right? So 78% plus 7% gives you 85%. So it's an effect size of 7%. How much of improvement does executive want? 7%, and this person would be happy. So now we're ready to show you a type 2 error, how it occurs. So this is null scenario. What do I mean by this? Well, look, the center here, closely, I try to do my best here, let's see. That's 78. So that is this null. So the center is at 78 right here. Okay. And there's a certain spread to this. I just kind of made something up right now. It is important, by the way, the spread, you can find out, but I want to make this as clearly visible as possible. So this is 78%. Now, so this is my null This is the model based on the null. But what is this one right here? It's one underneath it. Well, notice, look at the numbers. They're all lining up again. Look, 80, 80, 90, 90. So I made it so all these numbers are nicely lining up across. So I'm going to call this reality 2. This is the null scenario is I'm going to call reality 1. Okay, meaning that's the one that we're working with. Okay. And under this reality, we have a certain alpha value, which I haven't denoted, but there's some value, alpha, that denotes their ability to reject. To make my life simple, I'm going to say that it's right here at 90. This is the rejection region. So this little area is alpha, and that is, again, reject. So anything beyond here is reject. So reject null. So if your p hat value lands in this region, this is all rejection. You can see there's not a very good chance you're going to land here if this is correct, but it can happen. Okay, so again, this is now a type 1 error. Okay, so this is type 1. But what is type 2 again? Type 2 occurs when we don't reject a null hypothesis, when in fact it is correct. Sorry, it is incorrect. So wait a minute, if it's incorrect, that means the null value is something else. And now that's where this is coming in. So this is a wish list. As if we can hit 0.85, we would be so happy. Okay, and so now the wish is to get to 0.85. So you notice this is reality 2, and look what's here. Look at the center here now is 0.85. So this is what I'm calling PA. The executive's wish is that this thing is 85%, and this is the curve now under reality 2, which is based on something we call a reality 1, because it's executive 1. Maybe alt reality 1. Yeah, we call it alt reality 1, alternative reality 1. But executive, that's 85%. Okay, notice. Now the reason I've lined everything up, and again, we're not going to do a calculation, is so I can show you a type 2 error. A type 2 error occurs when we don't reject a null, when the hypothesis is correct. Well, what does that mean? That means, see this curve right here? It's wrong. It doesn't even exist. This is just a figment of our imagination. It's not even here. But if our p hat value lands here, we will reject. So the chance, this p hat value could land here. But what's the real chance then of landing here if this is not correct and this is correct? So now we come over here, and so this right here now becomes the real chance of seeing a p hat value land in this region. Okay. But remember, what is a type 2 error? When we don't reject the null hypothesis. So now we've got to understand that, well, this is the reject null region. Everything here is don't reject null. So don't reject is everything on the other side of this line. But what's the chance of that happening? It's right here. So this region here is probably of a type 2 error. This is the region right here, type 2. It has a name too. I might as well just give it to you. The probability of a type 2 error is symbolized by the Greek letter beta. But this region here is a chance of a type 2 error. So if you notice is that, okay, we made the type 1 error very small. But it turns out type 2 error is dang large. Like, what's the chance that we don't reject a null when in fact it is incorrect? Well, if PA happens to be 0.85, 85%, then under this scenario, you have a really good chance that you're not going to reject if this is really true. Okay. So notice there's another executive. I'll call this executive 2. And what an executive 2 goes, well, something 85% is just not that good. So in fact, notice this probability of type 1 error for beta. I'm going to do one more thing. So I can see this from this picture that whatever beta is, it's bigger than 50% because this whole area is type 2 error. So that's over half of the picture. So we know that much. But what about executive 2? Well, executive 2 says, yeah, that's a little not good enough for me. I wouldn't be happy with 0.85. I want to see 90% or better. I'm super happy. Under executive 2, this is 90. PA, another alternative possible value for, but this is under executive 2. I call this alt, reality 2. So now notice what's the chance of a type 2 error? Well, now it's a 90, so it's going to be, in this case, notice beta is going to be 0.5. It's half the picture, so I made this on purpose. So we can actually write a number down here. But you'll notice again that as the effect size, notice now the effect size for this is much bigger. The difference between 90 and 78 is 12. really, these are percentages, so 12%. So this is my effect size. As the effect size goes up, the probability of a type 2 error goes down. You can see that because we're getting further away, so there's less likelihood from this. We're getting further away from this. As the type 2 error does go down. But that seems kind of weird because, I mean, the goal is not a type 1 or type 2 or anything. It's to figure out what's really going on, the reality. But this really sets things up because now we start to understand that, let's say that you wanted to do a hypothesis test. What is it you would need to do? You would need to determine what the effect size that you're looking for is. You would then find, you determine an alpha level. But doing these things will eventually allow you to calculate type 2 and other things. But all this, what really, what you're going to use all this for is to determine n. So how do you determine n here for hypothesis testing? You're seeing the setup. Okay, so again, we're not going to calculate any of this, but we need to figure out, again, what effect size are we looking for to find? And that would eventually lead us to what sample size we need in order to do what we want to do. So this is the equivalent of finding the margin of error, and this is the equivalent of finding the confidence level when we take confidence intervals. Okay. So I'll do it one more time. What I've done is I've quadrupled the sample size. Whatever n was here, so n was some value, I've quadrupled sample size. Same scenario, but I decided I'm going to quadruple it. So what happens when you quadruple the sample size? Variation is divided in half. So there it is. There's my 78 again from the null hypothesis. And I'm still going to reject, notice the alpha level. So again, this looks about right. This 84 right here is where it looks about the same area. So this is your alpha. Okay. And here's exec 1. Here is exec 2. How do these two fare now? Well, that's alpha. I bring it down. So, I didn't line these up very good, did I? Oh yeah, a little shift here. Okay. I didn't line these up. Damn. Okay, there's the 84. So here. There is alpha, but notice this is now beta, which is a type 2 error. Okay, a chance of a type 2 error. And what do you notice happened now? Well, because I've quadrupled the sample size, notice my type 2 error has gone down. I went from over 50%. So now beta here, and you can see that it's going to be some value less than half. What about exec 2? And they're 90%. Well, again, following this trend, there's 84. And look at this. Exec 2 now is, I don't know what this value is, but it's certainly much smaller than it was before. Okay, well, what's the lesson here? In order to bring down type 2 error, we can increase the sample size in order to make that a reality. So by increasing the sample size, we're making the variability tighter, and then there's less overlap. So you can see the problem here is the overlap between these curves. Only one of these curves is correct. Okay, we don't know. In fact, we'll never know exactly, but this is the kind of calculation we want to do in order to determine what would be an appropriate sample size. Okay, so notice one thing that will also happen as we increase type 1 error. So notice if we increase type 1 error, that means moving over here. Notice making alpha bigger. We decrease type 2 error. And what's the remedy for trying to do both? Like, keep things stable? Increase sample size. So as we increase sample size, we decrease chance of making type 2 error. Notice it doesn't quite do anything for type 1 because we set that thing. This is kind of a weird thing, but this is just something we set. And here's kind of the last piece I want to kind of leave with you. Why do we care about setting type 1 or type 2? Because if we fail, if we set this so this is very low, the chance of committing a type 2 error is very low. right? So we set it up, it's very low to commit type 1 error. So we run the test, we fail to reject the null hypothesis. That means because we made the type 2 error small, we're more apt to believe that, remember, it's not just about reject or not reject, it's about meeting a goal. Let's say that that's the goal right there for the exact 2. So that means that we're now feel better that our procedure did not reach this goal. Okay, so that's the idea here. So sure, maybe it did increase, but it didn't meet our goal. And that's why doing these type of calculations is so important. So again, notice as we increase this one, we decrease this one and vice versa. If we decrease this one, we increase the other one. But one thing we could do is increase the sample size and then things will separate better. All right. Looking at a particular airline's records, it shows that during some months, but the same scenario as always, what would occur to commit a type 2 error? So a type 2 error is this. Again, let's read again. Occurs when we don't reject the null hypothesis. So we don't find evidence that the process has increased the on-time arrivals. Rate. We don't find evidence that the process increased the on-time arrival rate when in fact, so we don't reject the null hypothesis, when in fact is incorrect. The process has improved it. So again, one more time. So the importance of doing this is that if we fail to reject the null hypothesis, and we know that this thing was set up so it's small, then instead of saying, hey, the null hypothesis is correct or not correct, we can say, hey, there's a low chance we haven't even met our goal. Our goal was to get to 90% and we haven't met that. It brings a little more reality into what we can say with the results. That is a little more satisfactory. This is one last example. So researchers are wondering if eating dark chocolate will increase the average amount of antioxidant levels in the body. Suppose that the average amount of antioxidants in a group of patients deemed to be 0.37 mmol/P, whatever that is. And notice right now, again, we just want to show you that we can do this for means or proportions. This is just an idea. So right now we're doing, these are measurements. These are not proportions. We're just calculating the mean. And let's say that the mean level for the patients is 0.37 moles. And what we're trying to show is that somehow that if they start eating this dark chocolate, it will increase the amount. The significance level is set to 4%. So what does a type 1 error indicate in this scenario? Well, a type 1 error is we reject the null hypothesis when in fact we should have. So we find evidence that the dark chocolate has increased antioxidant levels on average when in fact it does nothing. Okay, that's what a type 1 error is. What does type 2 error indicate? So it's the exact opposite. We find evidence so again, look over. We don't reject the null hypothesis. Sorry, we don't find evidence. That dark chocolate increases antioxidant when in fact it does. Okay, so that's going to be a type 2 error. Again, type 2 occurs when we don't reject the null hypothesis, when in fact it is incorrect. So again, looking at this, it just says we don't find evidence that the dark chocolate increases the antioxidant level. In fact, it does. And that's really it. So just to recap, again, by increasing the sample size, it does get us closer to what is the true parameter. Okay, that's the one takeaway. Here, when sample sizes are smaller or if there's a lot of overlap, then it will be hard to make these detections. Like even if this is true, it'll be hard to figure that out because there's not enough separation between these two curves. Only one of these is right, but again, notice this huge don't reject region is part of the graph too. So if this is the reality, it's easy for a number to land here, which means we don't reject. In fact, but this is the actual graph, not this one. The same thing here, even this one's a little further out, but again, all this is the don't reject region, but shoot, there's a 50% chance that you're still gonna, even though if this graph is the correct graph for the situation, there's a 50% chance that we're gonna stay with this one, which happens to be incorrect. So well, once we increased the sample size, in this case quadruple it, everything got divided in half, and now there's bigger separation. So notice if this is the reality, there's a really good chance we're gonna be able to detect which one is right. Like, just is this the correct reality or is this the correct reality? So just a takeaway from this class.